Welcome back to Chapter 17, Part 4, Inferences about a population mean when population standard deviation is unknown. In this segment, we're going to talk about tests of significance. So, when we don't know the population standard deviation, we're once again in one of the t distributions, where our standard error is our sample standard deviation divided by the square root of n. So when we do our t statistic in a significance test or hypothesis test, our test statistic will look like the sample mean minus the null hypothesis distribution mean divided by the sample standard deviation from our sample divided by the square root of our sample size. And this t follows that t density curve with n minus 1 degrees of freedom. And the p-value of t is determined from that curve. The p-value is exact when the population distribution is normal and approximate for large n in other cases. So how we find the p-value is the same technique as when we used for the z. The only difference is that we have to use the t-tables, and that makes it a little more difficult. And we'll go over that and you'll see what I mean. But the idea is the same. If my sample mean is far out into the tails, we're going to end up rejecting the null hypothesis, and that p-value will be a value in which we can determine whether it's far out in the tail or not. So looking at this, the one sample t-test, looking at finding the p-values for the different test statistic depending on the alternative hypothesis, meaning whether we're in a right, left, or a two-tailed test. So we're going to go back to the sweetening colas problem that we saw in Chapter 14, except for in this chapter, there is no population standard deviation given. The problem goes like this, that you read here, and we see that we found 10 tasters for the new cola, and if you remember in Chapter 14 how it went, if the taster tasted the drink before and then after 2 weeks storage and said whether it lost sweetness, and the higher the number we got, the more it lost sweetness. So here's the data from 10 different tasters of this new cola. Now what we're asking is, are these data good enough evidence that the cola lost sweetness during storage? And we're going to do this at a 0.05 significance level. So right now we don't have any information at this point. The only thing we have is raw data. So we only have 10 pieces of raw data. We don't know anything about the about the distribution, so therefore we're going to have to do a probability plot and a box plot. We could also do a stem and leaf and a dot plot, but the two that we're going to use in our class is the probability plot and the box plot. So let's take a look. From here we see from the probability plot and the dot plot that there are no major deviations from normal. So we have reason to believe that the data comes from a population that's approximately normally distributed. And remember, when you do these plots, make sure you have meaningful titles, and there are the commands that you would use to get both of those plots. Now let's take a look at how we would do this problem by hand. The first thing we need to do is state the null and alternative hypothesis. And we said that if the cola lost sweetness, the number would be greater than 0. So that's our alternative. We think the null says that the drink did not lose any sweetness, so mu is 0. And the alternative saying that we think that it did lose sweetness, that's what we're testing at a 0.05 significance level. So step number 2 was to state the significance level, which again we just said was 0.05. How do we find the test statistic? Well, it's x bar minus mu naught over s divided by the square root of n. So we just put our numbers in. Where did the 1.02 come from and the 1.196? Well, that came from doing a data summary either in MINITAB or on a statistical calculator. So the 1.02 that you see, that's x bar. On our test, that will be given to you, and so will s. Or you'll have an output from MINITAB, and you can get those numbers off of there. So I put in my sample mean. Again, it would be given, I put that data in MINITAB, I would have found the sample mean minus 0. That's the null hypothesis distribution value for the mean, divided by S. Again, we got that from MINITAB, 1.196, divided by the square root of the sample size, which was 10. That gives us a value of 2.70, a test statistic of 2.70. Just by looking at that number, we're talking about being almost 3 standard deviations away. One would think that that would be somewhat unusual, and there's a real good chance we're going to reject the null hypothesis. But we can do this and be specific because we know what alpha, we're an alpha of 0.05. Let's see if we can find out what the p-value is. Well, the way to get the exact p or the approximate p-value, you'd use MINITAB, and you'd get 0.012, or in this case 0.0123. But if you only had the chart to go to, we have a little bit more trouble there because our chart doesn't give us, we can't find a t-value for 9 degrees of freedom of exactly 2.70. So how would we do this? So we look at our t-chart. Now remember, our test statistic is 2.70. For 9 degrees of freedom, we don't see that test statistic. We don't see that t-value. We see a number just more than it and just less. So we see 2.398 and 2.821. 2.7 is in between those two numbers. So the only thing we can do is capture our p-value. Now, how do we do that? Well, if we look up from the 2.398, that is the 96% confidence interval. That means in between 2.262 and negative 2.398 and negative 2.398, we have 96% of our data. So in the tail ends, how much would be left? Between the two tail ends, you have 4%, so we divide that into 2. So 2% will be to the right and 2% will be to the left. So our alpha for 2.398 is 0.02. Now, the alpha that goes with 2.821, that's a 98% confidence interval. So that means I'm going to have 1% on the upper tail and 1% on the lower tail greater than that confidence interval. And that means that the p-value that goes with 2.821 is going to be 0.01. So what we're going to say is our p-value has to be between 0.01 and 0.02 when we capture that. And that's what they're talking about on the second line up. That p-value is between 0.01 and 0.02. Since 2.7 is between 2.398, that has a p-value of 0.02, and the 2.821, which would have a p-value of 0.01. So we could only capture it. But if you look by technology, the p-value was 0.0123. That is definitely in between those two numbers, so it all works out. But even if we just knew that the p-value is between 0.01 and 0.02, we know then that that p-value is definitely less than 0.05. So from that, just even capturing it, we know we're going to reject the null hypothesis. As well as if using the computer getting the more exact answer of 0.0123, we see that that p-value is less than our alpha of 0.05, and we would reject. So that leads us to step 5, the conclusion. Since the p-value is smaller than 0.02, there is strong evidence that the new cola loses sweetness on average during storage at room temperature. So our interpretation, which is very important, this is what you're going to need for your MINITABs, at a 0.05 significance level, there is sufficient evidence to support the claim that the cola lost sweetness during storage. And here's a nice picture of what's going on with the t-distribution of 9 degrees of freedom. We have that t, our test statistic of 2.70, and the probability that any other sample would have a test statistic there or greater is 0.0123. Not a lot of probability on that. Or the other way that we look at a p-value, it's the probability of making a type 1 error based on our sample. And so the probability of making a type 1 error is 0.0123. Since that's less than the alpha that we had chosen, we said we would only make a mistake 5% of the time or less. Well, we're doing it here. Our sample tells us we'll make a error 5% or less. In fact, it tells us we're going to make it less than 2% of the time. There's the MINITAB commands that we would use for this test and the answer, and we can see it all comes out to be exactly the same. So that concludes this section of Chapter 17.